When you first look at a C++ project, you might notice something immediately. There are a lot of files. You see .hpp files, .h files, .cpp files, and sometimes even .cc or .cxx. If you've worked with languages like Python or JavaScript, where a single script often contains everything, this multi-file structure can feel a bit overwhelming. You might wonder why C++ insists on this separation. This isn't just about organizing your code into neat folders, although that's a nice side effect. This fundamental design choice is what gives C++ its incredible performance and allows for massive, complex software systems to compile efficiently. It's an invisible wall, a core architectural decision that dictates how your code is built and executed. Today, we're going to tear down that wall and see what's really happening. By the end of this lesson, you'll be able to confidently distinguish between header and source files, understanding their distinct roles in a C++ project. You'll grasp the concept of a translation unit and trace its journey through the entire build process. We'll tackle the infamous one definition rule and learn how to use include guards to prevent frustrating errors. Finally, you'll deconstruct a minimal C++ program, understanding exactly how it starts and finishes execution. Let's start with an analogy that helped me immensely when I was first learning this. Think about building a house. Before any bricks are laid or walls are framed, an architect creates a blueprint. This blueprint describes the house's layout, the number of rooms, where the doors and windows go, and the dimensions. It tells you what the house will look like and how you can interact with it, but it doesn't contain the actual materials or the construction process. The blueprint is the interface. It's the public-facing contract, the actual construction, the pouring of the concrete, the hammering of nails, the wiring of electrical systems. That's the implementation. You don't need to see the detailed wiring diagrams to know where to plug in your toaster. You just need to know there's an outlet there. C++ uses this exact same separation for your code. On the left, you have the blueprint, the design, the what. This is your header file. It declares what functions exist, what classes are available, and what variables you can use. It's the contract. On the right, you have the actual house, the how. This is your source file. It contains the concrete instructions, the actual function bodies, and the detailed logic. The header file, typically ending in .hpp or .h, contains declarations. It's like a table of contents for a library. It tells you that a function called add exists and takes two integers, returning an integer. But it doesn't tell you how add actually performs the sum. The source file, usually .cpp, contains the definitions. It's the actual book in the library, holding the full implementation of add. Let's look at a concrete example. Imagine we're building a simple math utility. We'll need a way to declare our functions and then define them. I'll show you the header file first. Here's our math_utils.hpp header file. The first line, #pragma once, is an include guard, which we'll discuss in detail shortly. This line declares two functions, integer add, parenthesis integer a, comma integer b, close parenthesis, semicolon, and double square root, parenthesis double x, close parenthesis, semicolon. Notice the semicolon at the end of each line. These are just declarations, function prototypes. They tell the compiler, hey, these functions exist, and this is their signature. The compiler now knows that if it sees a call to add parenthesis 5,7 close parenthesis, it's a valid function call, and it expects an integer return. It doesn't need to know how add works yet, only that it exists and what its parameters and return type are. This is crucial for allowing different parts of your program to use these functions without needing to see their full implementation. Now, here's the corresponding source file, math_utils.cpp. The first line, #include quote math_utils.hpp quote, brings in those declarations we just saw. This is how the compiler knows what add and square root are when it encounters their definitions. Then, we have the actual function bodies, integer add, parenthesis integer a, comma integer b, close parenthesis, open curly brace, return a plus b, semicolon, close curly brace, and double square root, parenthesis double x, close parenthesis, open curly brace. Implementation here, return 0.0, semicolon, close curly brace. These are the definitions. They provide the concrete instructions for what happens when add or square root is called. The compiler now sees the full picture for these functions. This separation is not arbitrary. It's a performance optimization. If I change only the implementation of square root in math_utils.cpp, I don't need to recompile every file that merely uses square root. This leads us to the first major reason for this separation, compilation speed. When you change a single line in a source file, only that specific source file needs to be recompiled. Headers, however, are often included by many source files. Keeping headers minimal and stable means fewer files need to be recompiled across your entire project, drastically reducing build times for large code bases. The second reason is modularity. The header file acts as a clear, concise interface. It tells other developers or other parts of your own code exactly what a module does without revealing the internal complexity of how it does it. This promotes cleaner design, reduces dependencies, and makes your code easier to maintain and understand. It's a contract, not a blueprint for every screw and nail. Now that you understand the difference between declarations and definitions and why they're separated, let's talk about the fundamental unit of compilation in C++, the translation unit. This is where the compiler actually gets to work. Imagine you have a main.cpp file that includes math_utils.hpp. When you compile main.cpp, the preprocessor first takes main.cpp and literally copies the entire content of math_utils.hpp into it. It's a text substitution. All those hash include directives are resolved, and any macros are expanded. The result is a single, massive file. This single, preprocessed file is what we call a translation unit. The compiler then takes this translation unit and compiles it independently into an object file, typically ending in .o or .obj. The crucial point here is that the compiler, at this stage, has absolutely no knowledge of any other translation units in your project. If main.cpp calls add parenthesis 5,7 close parenthesis, the compiler sees the declaration for add from the included header, so it knows the call is valid. It generates machine code that says, call the function named add, but it doesn't know where add actually lives in memory. That's a job for a later stage. This independent compilation allows for parallel builds, where multiple source files can be compiled simultaneously, speeding up your overall build process significantly. This independent compilation model brings us to one of the most important rules in C++, the one definition rule, or ODR. It states that every function or variable you use in your program must have exactly one definition across the entire program. Declarations, however, can appear multiple times. This distinction is critical. If you define a function or a global variable in a header file, and that header file is included by two different source files, then after preprocessing, each of those source files will contain a definition of that function or variable. When the linker tries to combine the object files generated from those two source files, it will see two definitions for the same entity. This is an ODR violation, and it will stop your build cold. Let me show you a common mistake. Imagine we forgot our include guard in math_utils.hpp, and instead of just declaring add, we actually defined it directly in the header file. So, integer add, parenthesis integer a, comma integer b, close parenthesis, open curly brace, return a plus b, semicolon, close curly brace is in the .hpp. Now, let's say we have two source files, main.cpp and another underscore file.cpp, and both of them hash include quote math_utils.hpp quote. Each translation unit, main.cpp and another underscore file.cpp, will independently compile fine because it only sees one definition of add within itself. But when the linker tries to combine main.o and another underscore file.o, it finds two separate definitions for the function add. This is a direct violation of the one definition rule. When you try to compile and link this, you'll get an error message that looks something like this. LD:error: duplicate symbol: add, or multiple definition of add parenthesis integer comma integer close parenthesis. This is the linker telling you, hey, I found two different places trying to define the same function, and I don't know which one to use. This is exactly why we use include guards. Include guards ensure that the contents of a header file are processed by the preprocessor only once within a single translation unit. They prevent duplicate declarations, which in turn prevents ODR violations if you accidentally define something in a header, or if a header itself includes another header that you've already included. There are two main ways to implement include guards. The traditional method uses preprocessor directives, #ifndef, #define, and #endif. This stands for if not defined, define, and endif. Here's how it looks. #ifndef math_utils_hpp_ checks if math_utils_hpp_ has been defined. If it hasn't, the preprocessor proceeds to the next line, #define math_utils_hpp_, which defines it. Then, the rest of your header content follows. Finally, #endif closes the conditional block. The next time this header is included in the same translation unit, math_utils_hpp_ will already be defined, so the preprocessor skips the entire content, preventing duplicates. The name math_utils_hpp_ is a convention, usually the file name in all caps, with dots replaced by underscores and a trailing underscore. It needs to be unique across your entire project. This mechanism ensures that even if you include the same header 5 times in one source file, its contents are only ever seen once by the compiler. The simpler, more modern approach is #pragma once. This is a non-standard but widely supported directive that achieves the same goal, ensuring the file is included only once. I use this almost exclusively because it's concise and less error-prone than manually managing ifndef blocks. Just put it at the very top of your header file, and the compiler handles the rest. So, we've talked about source files, header files, translation units, and the compiler. But how do all these pieces come together to form a runnable program? This is where the linker enters the picture. You start with multiple source files, like main.cpp, math_utils.cpp, and perhaps a graphics.cpp. Each of these, along with their included headers, forms a translation unit. The compiler processes each translation unit independently, producing separate object files, main.o, math_utils.o, graphics.o. These object files contain machine code, but they're not yet executable programs. They have placeholders for function calls that are defined in other object files. For example, main.o might have a placeholder for add, which is defined in math_utils.o. The linker's job is to resolve these placeholders. The linker takes all these object files, along with any necessary standard libraries, and stitches them together. It finds where add is actually defined in math_utils.o and replaces the placeholder in main.o with the correct memory address. If it can't find a definition for a function that was declared, you get an undefined reference linker error. Once all references are resolved, the linker produces a single, executable file, like my program. Now that you understand the entire build process, let's bring it all together with the simplest C++ program you can write. Every C++ program, no matter how complex, starts execution in one specific place, the main function. Here's our minimal hello.cpp program. The first line, #include angle bracket IO stream angle bracket, tells the preprocessor to include the contents of the IO stream standard library header. This header contains declarations for input and output stream objects, like standard cout for printing to the console. Next, integer main, empty parenthesis, open curly brace, ellipsis, close curly brace defines our entry point. The operating system starts your program by calling this main function. The integer indicates that main will return an integer value to the operating system, typically 0 for success and a non-zero value for an error. Inside main, standard cout left shift hello world, left shift standard end L, semicolon prints the string hello world to the standard output. Standard end L inserts a new line character and flushes the output buffer. Finally, return 0, semicolon signals to the operating system that the program executed successfully. This simple example already uses standard libraries, namespaces, streams, and operator overloading. To compile this, you typically use a command like g++ space dash standard equals C++20 space hello.cpp space dash o hello. Here, g++ is our compiler driver, dash standard equals C++20 specifies the C++ standard, hello.cpp is our source file, and dash o hello tells the linker to name the output executable hello. Once compiled, you run it from your terminal with ./hello. The operating system loads your executable, finds the main function, and begins execution there. The program runs, prints its message, returns 0, and then the operating system reclaims its resources. When you run this, you get exactly this on screen. Hello world. That's it. A complete C++ program, from source code to execution, leveraging the entire build process we just discussed. Today, you've learned to differentiate between C++ header and source files, understanding their distinct roles as interface and implementation. You now grasp the concept of a translation unit and how the compiler processes it into an object file. Most importantly, you can identify and resolve one definition rule violations using include guards, preventing those frustrating linker errors. You also trace the execution flow of a minimal C++ program, from the operating system calling main to its successful return. This foundational knowledge is crucial for writing robust, maintainable, and efficient C++ code. You are now equipped to understand why C++ projects are structured the way they are. For a challenge, try to create a small project with 2 source files and 1 header file. Define a function in one source file, declare it in the header, and call it from the other source file. Then, intentionally break the one definition rule by defining a global variable in the header without an include guard, and observe the linker error you get. This hands-on experience will solidify your understanding. Next time, we get our hands dirty with the actual building blocks of every program. Anatomy of a C++ program. Syntax fundamentals.